The brutal winds above the English Channel had been draining fuel at a terrifying pace. Second Lieutenant William E. Roach from the 358th Fighter Squadron, 355th Fighter Group, watched his fuel gauges plummet toward zero. His Pratt & Whitney R2800 engine started coughing and sputtering like a dying animal. The choice before him seemed impossible. England lay ahead, tantalizingly close but hopelessly distant given his fuel situation. The safety of home beckoned just beyond reach. Below him spread the French countryside in patches of green and brown. Some fields held friendly forces. Most crawled with German troops. One particular airfield caught his attention. It looked remarkably similar to the Allied bases he knew so well. The runways seemed familiar. The layout appeared standard. Roach made his decision and committed to the approach. His massive Republic P-47D Thunderbolt bore the serial number 4222490. The crew had nicknamed her Beetle. She touched down on the grass field with surprising smoothness for such a heavy aircraft. The wheels rolled across the turf without drama. Roach followed a ground vehicle toward what appeared to be a normal parking area. He shut down his engine according to standard procedure. The massive radial motor wound down with its characteristic rumble. Only then did he notice the distinctive markings on nearby aircraft. Balkan crosses decorated wings and fuselages all around him. His heart sank into his boots. German soldiers materialized from multiple directions. Rifles pointed at his cockpit from every angle. The muzzles looked enormous from his perspective. Lieutenant Roach's war as a combat pilot had ended in the most unexpected way possible. The remainder of the conflict would find him behind the wire at Stalag Luftwaffe. But something else was about to begin. The education of the German Luftwaffe would unfold in ways neither side could have anticipated. What German engineers would discover when they examined Beetle would shake their understanding of American industrial might to its core. The P-47 Thunderbolt represented far more than just another fighter aircraft. It embodied a complete philosophy of American engineering. It demonstrated production capabilities that defied easy comprehension. It showcased material abundance on a scale that seemed almost wasteful to German eyes. Over the following 18 months, German engineers would methodically tear apart captured Thunderbolts. They would test every system. They would fly the aircraft extensively. They would measure every component with precision instruments. What they learned would confront them with an uncomfortable reality. Germany had not simply fallen behind in some technological race. They had been competing in an entirely different category of warfare. The Americans were playing by rules that German industry could barely comprehend, much less match. The story of captured P-47s in German hands reveals the crushing weight of material superiority. When properly applied to military aviation, such overwhelming abundance could render tactical excellence increasingly meaningless. Pilot skill, no matter how refined, could not overcome such industrial disparity. The Thunderbolt would teach German engineers lessons they desperately needed, but they would never possess the resources to apply what they learned. Their nation lacked the materials, the infrastructure, and most critically, the time to implement what American factories treated as standard equipment. The capture of William Roach's P-47 on November 7, 1943, was not the Luftwaffe's first encounter with the Thunderbolt. German pilots had been tangling with the massive American fighter since April 1943. That was when the 4th Fighter Group first escorted B-17 bombers into hostile airspace over occupied Europe. Initial impressions from Luftwaffe combat reports reflected a strange mixture of contempt and confusion. German pilots were accustomed to nimble aircraft. The Focke-Wulf 190 and Messerschmitt Bf 109 danced through the sky with agility that seemed almost supernatural. The American fighter appeared absurdly large in comparison. At low altitudes, the P-47 seemed sluggish and unresponsive. It appeared designed by engineers who had never considered the requirements of aerial combat as the Luftwaffe understood them. The massive radial engine looked primitive compared to sleek German inline power plants. Combat reports from German fighter units throughout spring and summer 1943 consistently noted problems with the P-47. Its rate of climb seemed pathetic compared to German fighters. Its handling at lower altitudes appeared ponderous and clumsy. Most telling, American pilots seemed reluctant to engage in traditional turning dogfights. The initial assessment among experienced Luftwaffe pilots was damning. The Thunderbolt represented inferior design thinking. It could be outmaneuvered at medium altitudes where most combat occurred. Any competent German pilot should be able to defeat it in single combat. This assessment would prove catastrophically incomplete. But other details in those same combat reports hinted at something more troubling. These observations contradicted the narrative of American inferiority in subtle but important ways. Pilots described how Thunderbolts that chose to disengage from combat simply could not be caught. Once they entered a dive, pursuit became hopeless. The American fighters would accelerate to speeds that left German aircraft struggling far behind. They mentioned 8 heavy machine guns that fired with devastating effect. When American pilots did choose to engage, the volume of fire was simply overwhelming. No German fighter carried equivalent firepower. The weight of metal thrown through the air was staggering. They noted armor protection that seemed impervious to standard ammunition. The 7.92mm rounds that could damage German fighters often bounced harmlessly off American armor plate. Even 20mm cannon fire frequently failed to achieve decisive results against Thunderbolt protection. Most disturbingly, they reported that even badly damaged Thunderbolts continued flying. Aircraft with battle damage that would have destroyed any German fighter kept flying. They limped back to England, missing sections of wings. Engines streamed oil through shot-up cooling systems. Control surfaces hung by cables. Yet the pilots maintained control. Damaged P-47s routinely returned to base in conditions that should have been impossible. Some landed successfully despite damage that looked unsurvivable. The structural strength seemed to exceed anything in German experience. When Lieutenant Roach's intact Thunderbolt rolled to a stop at Carpiquet, the Luftwaffe finally had their opportunity. They could examine in detail the aircraft they had been consistently underestimating. Local Luftwaffe personnel immediately recognized the intelligence value of a complete, undamaged example. Within hours, Beetle was surrounded by armed guards. They prevented any sabotage or accidental damage. American markings disappeared under fresh paint. German Balkan crosses appeared on wings and fuselage with military efficiency. Bright yellow identification paint was applied to undersurfaces and tail surfaces. This yellow paint followed standard Luftwaffe practice for all captured aircraft. The color designation was RLM-04 yellow. It prevented friendly fire from German anti-aircraft gunners who might otherwise shoot down their own evaluation aircraft. Shortly after capture, arrangements were made for transfer to Rechlin. This was the Luftwaffe's premier testing facility. It sat approximately 100 kilometers northwest of Berlin in Mecklenburg province. The aircraft received the designation T9 Pulse FK. This coding identified it with the Circus Rosarius Evaluation Unit. Hans-Werner Lersche was assigned to conduct initial evaluation flights. He served as principal test pilot and chief engineer at Erprobungsstelle Rechlin. Lersche would ultimately fly over 125 different aircraft types during the war. He never crashed or seriously damaged a single aircraft in his care. Lersche approached the P-47 with professional curiosity tempered by appropriate caution. The aircraft's unfamiliar systems demanded respect. His first impression, documented in his logbook and later published in his memoirs, reflected surprise at the cockpit's complexity. The instrument panel contained what seemed like twice the number of gauges found in German fighters. Strange levers controlled systems Lurch had never encountered in German designs. The turbo supercharger system required understanding of exhaust flow management principles that remained largely theoretical in German aviation circles. In America, These principles appeared to be standard practice across their fighter designs. The constant speed propeller operated differently from German equivalents. Most confusing was the elaborate system of automatic engine management. German pilots handled such functions manually through constant throttle and mixture adjustments. Lerche wrote in his memoirs about the bewildering complexity. The P-47 cockpit could baffle even an experienced pilot. He gradually managed to ascertain the function of most levers and instruments, but there were also some obscure controls whose meaning was not immediately clear to him. He spent considerable time on the ground experimenting with controls. He studied the layout methodically before attempting flight. This testified to his methodical approach to test flying unfamiliar aircraft. He had no benefit of pilot manuals or operational documentation. The engine start sequence alone revealed sophistication beyond standard German practice. The Pratt & Whitney R2800 double wasp required specific procedures. The massive turbo supercharger system had to be properly initialized. Each step had to be followed in the correct sequence. Lerche followed the process methodically. His engineer's mind cataloged each step. He inferred the purpose of each action through careful observation. When the 18-cylinder radial engine roared to life, it produced a sound utterly different from German power plants. German inline engines had a sharp bark that pilots knew intimately. Even the BMW 801 radial that powered the FW190 sounded different. This was a deep, powerful rumble that spoke of enormous displacement. Tremendous power reserves were held in check, waiting to be unleashed. Lerche taxied carefully, feeling the weight of the aircraft through the controls. The P-47D weighed nearly 10,000 pounds empty. This particular example was still carrying substantial fuel and a full ammunition load. That brought the total weight closer to 13,500 pounds. For direct comparison, the FW190A was one of Germany's heaviest single-seat fighters. It weighed approximately 7,650 pounds empty. At maximum loaded weight, it reached roughly 10,800 pounds. The Thunderbolt was genuinely massive for a single-seat fighter. It was larger than some twin-engine aircraft in Luftwaffe service. Lerche advanced the throttle for takeoff. The difference between German and American engineering philosophy became immediately apparent. The R2800 developed 2,000 horsepower at standard boost settings. With war emergency power using water methanol injection, it reached 2,300 horsepower. Germany's BMW 801D was the finest radial engine in German production. It powered the FW190 and represented the pinnacle of German engine technology. It produced between 1,100 and 1,130 horsepower at maximum continuous power settings. Even with this power advantage, the P-47's greater weight meant the takeoff run was longer than Lerche expected. The aircraft consumed nearly the entire grass field at the transfer airfield. The massive fighter seemed to lumber into the air rather than leap skyward. But once airborne, Lerche began discovering why German pilots who had fought Thunderbolts only at low altitude had fundamentally misunderstood the aircraft's capabilities. He climbed steadily, nursing the turbo supercharger to operating temperature as altitude increased. Below 15,000 feet, the P-47 felt exactly as German combat pilots had described in their reports. It seemed heavy and sluggish in turns. It was unable to match German fighters in maneuverability. The rate of climb was mediocre at best compared to the FW190 or BF109. At this altitude range, any competent German pilot in a contemporary fighter could outmaneuver the Thunderbolt in sustained turning combat. The American fighter seemed to wallow through the air like a transport aircraft pressed into combat service. But somewhere above 20,000 feet, the character of the aircraft transformed completely. The turbo supercharger, driven by exhaust gases, became increasingly efficient as air pressure decreased with altitude. It began forcing massive quantities of compressed air into the engine cylinders. While German engines gasped for oxygen and lost power as altitude increased, the R2800 maintained full rated power. The automatic systems compensated for the thinning atmosphere without requiring pilot intervention. The engine breathed as easily at 25,000 feet as at sea level. At 25,000 feet, German fighters were operating at perhaps 70% of their sea-level power. The Thunderbolt's engine was still producing full-rated output. The playing field had completely reversed from the situation at lower altitudes. Lurch pushed the throttle forward at 25,000 feet and felt the Thunderbolt accelerate with surprising vigor for such a large aircraft. The massive fighter surged ahead with authority that belied its bulk. He rolled into a dive to test high-speed characteristics, and the aircraft responded with enthusiasm that bordered on violence. The P-47 accelerated past 500 miles per hour in a steep dive. It reached speeds where the controls stiffened dramatically as airflow compressed around the airframe. At this speed, recovery from the dive required both hands on the control stick. Considerable physical strength was necessary to pull out safely. The aircraft was approaching the limits of compressibility that would not be fully understood until the jet age. The airflow over the wings began behaving strangely at these speeds. Control effectiveness changed dramatically as shock waves formed over control surfaces. The roll rate impressed Lurch immediately and contradicted everything German pilots had assumed about the heavy American fighter. Despite its size and weight, the Thunderbolt could roll faster than any German fighter Lurch had flown. This included the FW-190, which was considered excellent in roll performance. This characteristic, combined with its devastating dive speed, created a tactical advantage that German pilots had been reporting without fully understanding the implications. An American pilot in trouble at high altitude could simply roll inverted and dive away at speeds no German fighter could match. Any Luftwaffe pilot attempting pursuit would encounter compressibility effects that the P-47's stronger airframe and more effective controls handled more successfully. The American fighter was designed to operate safely at speeds that could destroy German aircraft. Lurch flew the captured Thunderbolt through a comprehensive test program. He explored the flight envelope systematically according to standard Rechlin evaluation procedures. Every aspect of performance was documented with German precision. His preliminary report contained observations that troubled Luftwaffe headquarters staff who still believed German fighter designs were fundamentally superior. At altitudes above 25,000 feet, where aerial combat was increasingly occurring as Allied bomber formations flew higher to escape German flak, the P-47 Thunderbolt was not inferior to German fighters. It was superior in specific crucial ways that negated German advantages in maneuverability and rate of climb. The traditional German fighter tactics became ineffective against an opponent that could dictate the terms of engagement. Over the following weeks, Rechlin's engineers subjected Beetle to exhaustive testing according to standard Erprobungsstelle procedures. They photographed every component from multiple angles. They measured every dimension with precision instruments. They weighed every major part and assembly. They tested every system under various conditions, different temperatures, different altitudes, different power settings. Every variable was systematically explored and documented. The turbo supercharger system received special attention. This technology represented the primary difference between American and German approaches to high-altitude performance. German engineers had theoretical knowledge of such systems, but had never successfully implemented them in production aircraft. What they discovered in detailed examination shocked engineers accustomed to resource-constrained design philosophy. The Pratt & Whitney R2800 consisted of 18 cylinders arranged in 2 rows of 9 cylinders each around a central crankshaft. Total displacement measured 2,804.5 cubic inches, equivalent to 45.958 liters. For direct comparison, the BMW 801D displaced 2,560 cubic inches, or 41.8 liters. But displacement alone didn't explain the significant power difference between the engines. The materials and manufacturing quality told the real story. The R2800 incorporated forged aluminum alloy pistons that showed precision manufacturing to tolerances German industry struggled to achieve. Sodium-cooled exhaust valves handled extreme temperatures that would destroy conventional valves. The crankshaft was forged from high-grade steel alloy that German metallurgists examined with professional envy. They recognized materials they could no longer obtain in sufficient quantities. Strategic bombing had disrupted supply chains for exotic alloys. The Americans were using materials that Germany had been forced to abandon or reserve for the most critical applications. The quality of American materials and manufacturing precision astounded the German inspection team. Every component showed evidence of precision manufacturing to tight tolerances. Surface finishes were consistently smooth across all parts. No tool marks, no rough edges, no signs of hurried production. The magnetos used materials that were increasingly scarce in Germany. Copper windings were heavy and pure. The spark plugs incorporated high-grade ceramics of superior quality to German equivalents. The fuel injection system operated with precision that German engineers associated with laboratory equipment rather than combat aircraft. Most tellingly, the entire engine showed no signs of material substitution or quality compromise forced by resource limitations. The Americans had built this engine exactly as the designers intended. They had used all specified materials without the desperate improvisations that increasingly characterized late-war German production. The turbo-supercharger system revealed engineering sophistication that Germany had attempted to develop but never successfully implemented in production aircraft. Exhaust gases from all 18 cylinders were collected through manifolds and routed through insulated pipes running along each side of the fuselage to a turbine unit located behind and below the cockpit. This turbine, spinning at tremendous speed driven by hot exhaust gases, drove a centrifugal compressor that forced additional air into the engine's supercharger. The system included an intercooler to reduce the temperature of compressed air, thereby increasing its density and preventing destructive detonation. Automatic regulators controlled boost pressure and turbine speed without requiring constant pilot intervention beyond setting the desired manifold pressure. The pilot simply set the desired power, and the system maintained it automatically regardless of altitude changes. German engineers understood the theoretical principles perfectly. They had conducted experimental programs exploring similar approaches. But implementing such a system in mass-produced combat aircraft had proven impossible given material shortages and manufacturing limitations that plagued German industry by 1943. The turbo-supercharger required exotic high-temperature alloys for turbine blades that had to withstand extreme temperatures while spinning at high speeds. The control system demanded precision manufacturing and reliable components. The extensive ducting needed heat-resistant materials and perfect seals to function efficiently. Every element had to work reliably in combat conditions. They were exposed to vibration, temperature extremes ranging from -60 degrees Fahrenheit at altitude to over 200 degrees near the engine, and potential battle damage. The Americans had solved all these problems and installed the complete system as standard equipment on every P-47 produced. The turbo-supercharger was not experimental equipment reserved for special missions or limited production runs. It was simply how the airplane worked, installed in thousands of examples rolling off American production lines every month. This casual implementation of advanced technology as standard production equipment revealed an industrial capacity that German engineers found difficult to fully comprehend. The scale of American manufacturing exceeded anything in European experience. German technical reports from the Rechlin evaluation noted that the turbo-supercharger system alone represented a level of engineering sophistication and manufacturing capability that exceeded current German capacity to replicate in production quantities. The materials, the precision manufacturing, the quality control required to produce such systems reliably at scale simply exceeded what German industry could achieve in 1943. Strategic material shortages limited access to necessary alloys. Progressive degradation of manufacturing standards caused by Allied bombing campaigns disrupted production. The replacement of skilled workers with forced labor reduced quality control throughout the system. The armament installation provided another lesson in American abundance and attention to design details. The P-47D mounted 8 Browning M2 machine guns of 50 caliber with 4 guns installed in each wing. The installation was symmetrical and precisely engineered. Most German fighters of the period carried mixed armament, typically 4 machine guns and 2 20mm cannons, or in early models, 6 machine guns total. The American decision to install 8 heavy machine guns represented a deliberate choice to maximize firepower, even at the cost of additional weight and complexity. Each machine gun was fed from a separate ammunition box built into the wing structure. Each box contained 425 rounds of 50 caliber ammunition. Total ammunition capacity was 3,400 rounds across all 8 guns. The weight of this ammunition alone exceeded 400 pounds. For direct comparison, the FW-190A typically carried approximately 2,000 rounds total for its machine guns and 500 rounds total for its cannons. The P-47 pilot could fire all 8 guns continuously for approximately 20 seconds before exhausting ammunition, with the combined rate of fire approaching 100 rounds per second. When all 8 guns were properly harmonized to converge at a single point in space, the volume of fire was simply overwhelming to any target. No aircraft structure could withstand such concentrated firepower for more than a few seconds. German test firings of the captured aircraft's armament system documented the devastating effect. Targets simply disintegrated under the weight of fire. The installation quality impressed German armament specialists who examined the systems in detail. Each gun was mounted in an electrically heated bay to prevent freezing at high altitude where temperatures could drop to -60 degrees Fahrenheit or lower. Spent cartridge cases and disintegrating belt links were collected through chutes and ejected through ports in the wing's lower surface. This prevented them from damaging the aircraft or interfering with control surfaces. The system functioned flawlessly during Rechlin testing, despite firing thousands of rounds under varying atmospheric conditions. No jamming or feeding malfunctions were recorded throughout extensive testing. Ammunition quality also revealed another dimension of American industrial capability. The 50 caliber rounds used armor-piercing cores manufactured to consistent specifications. Incendiary compounds functioned reliably, and tracer elements burned predictably throughout their flight path. Testing revealed that American ammunition was consistently more reliable than equivalent German production, which had suffered quality degradation as strategic materials became scarce. Powder charges were uniform, primers fired consistently, and projectiles maintained their intended ballistic characteristics. The Thunderbolt's armor protection demonstrated American willingness to accept significant weight penalties in exchange for pilot survivability. This represented a philosophical difference from German design priorities that emphasized performance over protection. The cockpit was surrounded by heavy armor plate on multiple sides. The pilots sat in what American designers called an armored bathtub that provided protection from below and from behind. Critical areas were shielded by steel plate thick enough to stop machine gun rounds and resist cannon shell fragments. The windscreen incorporated thick bulletproof glass capable of stopping machine gun rounds and resisting cannon shell fragments. The glass was optically clear despite its thickness, showing advanced manufacturing techniques in laminated armor glass production. Additional armor plates protected critical systems including oil coolers and the vulnerable turbo supercharger components. Total armor weight exceeded 200 pounds, roughly equivalent to the weight of adding 2 additional machine guns with full ammunition loads. German fighters typically carried less comprehensive armor protection, prioritizing lighter weight and better performance while accepting higher pilot casualties as an unavoidable cost of combat operations. The German philosophy emphasized producing more aircraft rather than making each aircraft more survivable. The design philosophy difference revealed itself clearly in maintenance accessibility. American designers had clearly anticipated that mechanics working in forward air bases would need to service aircraft quickly, possibly at night, possibly under adverse weather conditions, possibly while under threat of enemy attack. Every major component could be accessed through large panels secured with quick-release fasteners that required only simple tools. The massive engine could be changed in the field within a few hours, using standard hoisting equipment and following clearly documented procedures. German fighters, designed with the expectation of factory-level maintenance for major repairs, typically required more extensive disassembly for major component service. This difference reflected American abundance versus German scarcity in engineering resources and manufacturing capacity. The Americans could afford to dedicate engineering resources to maintainability because their industrial capacity allowed them to optimize designs for operational efficiency rather than pure production efficiency. They could make aircraft easier to maintain because they had the luxury of abundant resources. The radio installation in the captured P-47 represented another area where American technology exceeded German equivalents. The aircraft carried an SCR-274N command radio for air-to-air and air-to-ground communication, plus an SCR-515A liaison radio providing additional communication channels. Both units operated with clarity and range that exceeded contemporary German radio capabilities. German radio systems suffered from persistent interference problems that American engineers had apparently solved through superior component design and better shielding techniques. The radios also integrated with an identification friend or foe system that automatically identified friendly aircraft to ground controllers, preventing friendly fire incidents. This level of automated identification represented sophistication that German forces lacked in 1943. Perhaps the most profound revelation for German engineers came not from any single advanced system, but from the cumulative impression of quality and completeness throughout the aircraft. Every component appeared to be the best possible version of that component that American engineers could design and manufacturers could produce. Nothing was obviously compromised due to material shortages. Nothing showed clear evidence of substitute materials being used because preferred materials were unavailable. Nothing reflected the desperate improvisations that increasingly characterized German late-war production as strategic bombing degraded industrial capacity and material shortages became acute. German technical reports compiled at Rechlin and distributed through Luftwaffe Technical Services emphasized this point repeatedly. The P-47 Thunderbolt had been built exactly as the designers intended, using all specified materials and processes with no apparent compromises forced by resource scarcity. This level of manufacturing fidelity to original design specifications was becoming increasingly difficult for German industry to achieve as the war progressed. American industry operated without such constraints, at least through 1944. The flight testing program continued through the winter of 1943 and into early 1944 as additional P-47s were captured and brought to Rechlin for comparative evaluation. Each aircraft provided additional data points for German intelligence analysis. On May 29, 1944, another P-47 landed in German hands when Second Lieutenant Lloyd S. Hathcock of the 301st Fighter Squadron, 332nd Fighter Group, became disoriented during a ferry flight and mistakenly landed at the enemy-held Rome Littorio airfield in Italy. His aircraft, serial number 4275971, was quickly seized by German forces who recognized the intelligence value immediately. This P-47 had previously been the personal mount of George Novotny, an 8-victory ace flying with the 317th Fighter Squadron. The Germans transferred the aircraft to Rechlin, where it was initially designated 8+6, then later transferred to Zircus Rosarius on October 12, 1944, where it received the designation T9 Pulse LK. Additional testing data accumulated from multiple aircraft strengthened the conclusions drawn from the first evaluation. The testing data accumulated at Rechlin produced tactical recommendations that were compiled and distributed to frontline Luftwaffe fighter units. These recommendations advised that engaging P-47s below 15,000 feet offered the best probability of success for German pilots. The Thunderbolt's poor low-altitude performance and slow rate of climb gave German fighters clear advantages in that altitude regime. Pilots were specifically warned to avoid diving away from attacking Thunderbolts, as the American fighter would simply accelerate to speeds that German aircraft could not match in a dive. The reports emphasized that damaged P-47s frequently continued flying despite battle damage that would destroy German fighters, so attacks needed to be pressed home aggressively with concentrated fire rather than assuming that a few hits would down the aircraft. But the tactical advice, however useful to individual pilots, could not address the fundamental strategic problem that became increasingly apparent as the evaluation progressed. The scale of American industrial might dwarf anything Germany could match. Each downed Thunderbolt vanished from American squadrons within mere days. New aircraft rolled off production lines at staggering rates. Over 300 P-47s emerged monthly from Republic aviation factories at peak production. Fresh pilots arrived in equal numbers from training programs that had compressed instruction time while maintaining quality. Germany could no longer sustain such replacement rates. Fuel shortages grounded training flights. Experienced instructors died in combat faster than they could pass on their knowledge. Behind American Thunderbolt operations stretched supply chains that seemed infinite. Fuel trucks arrived without fail. Ammunition stockpiles never ran empty. Spare parts flowed like water. Every component needed for sustained operations appeared exactly when required. German logistics crumbled under relentless Allied bombing. Supply convoys burned on cratered roads. Fuel depots exploded in spectacular flames. The contrast became painfully obvious to any observer with functioning eyes. Eventually, the captured P-47s found their way to Wanda Circus Rosarius. This specialized demonstration unit served the Luftwaffe in ways both practical and symbolic. Flugkapitän Theodor Rosarius commanded this traveling circus of captured aircraft. His teams moved constantly between frontline fighter bases across occupied Europe. German pilots gathered around American machines they had heard about but never seen up close. The demonstrations served education first. Recognition training mattered desperately when split seconds determined survival. But these sessions carried deeper psychological weight than anyone expected. Pilots studied visual details that could save their lives in combat. Wing shapes, engine cowling profiles, landing gear configurations. Every marking and antenna had meaning in the deadly game of aerial identification, yet they also witnessed disturbing truths about Allied technological superiority. The evidence sat before them in tangible form. These were not propaganda photographs or intelligence estimates. Real American fighters demonstrated real capabilities on German airfields. The psychological impact cut deep into Luftwaffe morale. Post-war interviews revealed how profoundly these demonstrations affected veteran pilots. Circus Rosarius crews could highlight certain advantages German fighters retained. Medium-altitude performance still favored domestic designs in specific circumstances. Turn rates at lower speeds sometimes gave German pilots tactical options, but the uncomfortable reality emerged clearly during each presentation. At the altitudes where American bomber formations operated with their P-47 and later P-51 escorts, German fighters struggled badly. The performance gap widened with each 1,000 feet of altitude gained. Intelligence data extracted from captured Thunderbolts shattered optimistic assumptions that had circulated through Luftwaffe briefings. Earlier war reports had understated American aircraft capabilities. Reality proved far more sobering than anyone had anticipated. Performance figures told the complete story in numbers that could not be disputed or rationalized away. At sea level, the P-47D managed approximately 350 miles per hour maximum speed. This seemed unimpressive compared to the FW-190A's 408 miles per hour at identical altitude. German pilots took some comfort from these low-altitude comparisons. At 10,000 feet, the Thunderbolt reached about 375 miles per hour. Still nothing revolutionary. But at 30,000 feet, the P-47 achieved 426 miles per hour. The FW struggled to reach 370 miles per hour at that same altitude. The Bf-109 managed approximately 385 miles per hour when pushed to its limits. The performance advantage at combat altitudes was devastating. No ambiguity existed in these measurements. The gap widened as altitude increased. Allied bomber formations climbed higher each month to escape German anti-aircraft fire. They could afford to fly where German interceptors could barely function. The service ceiling comparison provided equally grim reading for German tactical planners. The P-47 Thunderbolt operated effectively to 42,000 feet. German fighters rarely functioned above 35,000 feet. Performance degraded rapidly in the thin air that starved their engines of power. American bomber streams could and did operate at altitudes where German interceptors could barely reach them. The few German fighters that did claw their way to extreme altitude had no power reserves left for effective combat maneuvering. They arrived gasping and struggling. P-47 escorts cruised comfortably at these same altitudes. They maintained full combat capability while German fighters fought just to stay airborne. The tactical implications were crystal clear to anyone willing to face facts. Range comparisons revealed another dimension of American industrial and logistical superiority that German planners found deeply troubling. With external fuel tanks, the P-47D could escort bombers penetrating deep into the German heartland. Early P-47 models had suffered from limited range that restricted their effectiveness to shorter missions. But by 1944, Thunderbolts equipped with 108-gallon drop tanks routinely flew missions covering 1,000 miles or more. German fighters had been designed primarily for short-range interception missions defending the Reich. They lacked internal fuel capacity for extended operations beyond their own borders. This difference in operational radius meant American fighters could engage at times and places of their own choosing. They possessed tactical flexibility that German commanders could only envy. German fighters were forced into defensive postures. They had to react to American initiatives rather than setting their own terms of engagement. The psychological effect of always fighting on enemy terms wore down even veteran pilots over time. The captured Thunderbolts provided unique insights into American pilot training and tactical doctrine through careful examination of gun camera footage and analysis of combat damage patterns on aircraft that had survived battles before capture. The evidence revealed systematic approaches that impressed German analysts despite their implications. American pilots consistently employed tactics that emphasized the P-47's natural strengths while carefully avoiding situations that exposed its known weaknesses. They maintained high altitude where the turbo supercharger provided clear and decisive advantage over German opposition. They employed dive and zoom attacks rather than attempting sustained turning dogfights where German fighters held traditional advantages. They worked in coordinated pairs or four-ship flights rather than engaging in individual combat that German aces preferred. Mutual support took priority, even when this meant declining apparently advantageous individual engagement opportunities. The discipline evident in American tactical execution impressed Luftwaffe analysts who studied captured evidence with professional objectivity. Many Luftwaffe pilots, particularly experienced aces with multiple victories, preferred individual combat that relied on personal skill and aggressive tactics to achieve victory. American pilots appeared to follow established doctrine consistently. They supported each other systematically. They rarely allowed individual pride or aggressive instincts to override tactical common sense. This disciplined approach, combined with superior high-altitude equipment and growing numerical advantage, created a combination that even veteran German pilots found increasingly difficult to overcome as months passed and the war situation deteriorated. By D-Day in June 1944, the strategic situation had deteriorated to the point where intelligence gathered from captured aircraft provided little practical value to Germany's increasingly desperate war effort. The Luftwaffe understood clearly and completely that American equipment was superior in critically important ways. They comprehended American tactics through careful study. They possessed detailed technical data on Allied aircraft performance characteristics. But this knowledge could not magically produce the resources, strategic materials, manufacturing capacity, and trained personnel needed to compete effectively. The Rechlin reports were carefully compiled and professionally distributed throughout Luftwaffe technical services. They served primarily to document the technological and industrial gap that was driving Germany toward inevitable defeat. The numbers told a story that no amount of tactical cleverness could overcome. German engineers could measure the dimensions of their disadvantage with scientific precision. This knowledge provided no path forward, given the deteriorating industrial situation that constrained all German military production. The comparison between American and German engine production illustrated the impossible position Germany faced with stark mathematical clarity that allowed no room for optimistic interpretation. Pratt & Whitney, working alongside licensee Ford Motor Company, produced over 125,000 R2800 engines by war's end. Production of this single engine type exceeded Germany's entire combat aircraft engine production throughout the entire war. The scale disparity was almost incomprehensible to German industrial planners accustomed to resource scarcity. BMW managed to produce approximately 61,000 examples of the 801 radial engine throughout the entire war period. The Daimler-Benz DB605, Germany's most produced inline engine design, reached approximately 42,400 units total production from start to finish. American production of one advanced engine type surpassed Germany's total output of all combat aircraft engines combined from all manufacturers. The industrial mathematics were unforgiving and absolute. American industry in 1944 alone produced approximately 96,000 aircraft of all types, while Germany reached approximately 25,000 aircraft, including trainers and utility types. The United States produced 38,000 fighters alone that same year, plus 16,000 heavy bombers, plus thousands of medium bombers, transports, and training aircraft. When combined with British and Soviet production capacity, the Allied advantage in aircraft production exceeded 5-1 by 1944. The gap continued widening rather than narrowing as American production hit full stride. The industrial base supporting this massive production operated on a scale Germany could never hope to match given available resources and geographic constraints. The Aluminum Company of America alone produced more aluminum than Germany's entire aluminum industry from all sources combined. Individual American steel plants frequently outproduced the entire Ruhr industrial region that had been Germany's manufacturing heartland before Allied bombing began systematic destruction campaigns. Ford's Willow Run factory produced B-24 bombers using moving assembly line techniques, while German plants relied on batch production methods that required more skilled labor and longer production times. Even the machine tools that built the machines that built the aircraft were themselves produced in quantities that allowed American industry to supply not only its own requirements, but also substantial quantities to British and Soviet allies through Lend-Lease arrangements. The industrial ecosystem supporting American aircraft production included everything from raw material extraction through final assembly and delivery to combat units. Every link in this chain operated at scales that dwarfed comparable German capabilities. The captured P-47s ultimately ended their German service in the chaotic final months of the European War, when organized resistance collapsed and units scattered or surrendered. The aircraft designated T-9 plus FK, originally William Roach's Beetle, was recovered by American forces at Göttingen in May 1945. They found it among a collection of captured Allied aircraft that the Germans had been systematically evaluating for intelligence purposes throughout the war. Photographs taken by American recovery teams show the aircraft still wearing partial German markings, parked alongside FW-190s and BF-109s, in what had effectively become a museum of captured equipment. This collection documented the impressive breadth and thoroughness of the Luftwaffe's intelligence-gathering effort throughout the conflict. The Germans had been methodical and professional in their approach to understanding Allied capabilities. Unfortunately for them, understanding capabilities and being able to match or counter them proved to be entirely different challenges. The Thunderbolts that served with German evaluation units provided German pilots and engineers with an education they desperately needed, but had received too late to matter strategically. The war's outcome had already been determined by industrial factors that no amount of tactical knowledge could overcome. The aircraft demonstrated that American industrial philosophy prioritized absolute capability over elegant efficiency. Abundant resources took precedence over careful optimization. Systematic material advantage mattered more than individual technical excellence in isolated parameters. These priorities, when implemented with nearly unlimited resources and manufacturing capacity, produced weapon systems that outclassed German equivalents in the aggregate. This remained true even when German designs showed superior characteristics in specific isolated parameters that impressed engineers but had limited battlefield impact. The lesson extended far beyond the P-47 itself into broader questions of industrial warfare and national resource allocation during extended conflicts. Every category of captured American equipment told the same fundamental story to German analysts willing to face uncomfortable facts. The B-17 Flying Fortress bomber, with its quartet of turbo-supercharged Wright Cyclone engines, represented a strategic bombing capability Germany never achieved despite early advantages in aircraft design and pilot training. The P-51 Mustang, combining American airframe engineering with the British Rolls-Royce Merlin engine, created what many historians consider the finest piston engine fighter of the entire war period. The P-38 Lightning, with its twin turbo-supercharged engines and tricycle landing gear, demonstrated American willingness to pursue unconventional solutions when conventional approaches seemed inadequate. Each aircraft type revealed the same fundamental American approach to military aviation problems: solve technical challenges through superior engineering, supported by unlimited industrial capacity, rather than through clever optimization, constrained by chronic resource scarcity that had plagued German production throughout the war. Luftwaffe analysts clearly observed that they were not being defeated by superior tactics or better-trained pilots, though American training programs were producing adequate pilots in overwhelming numbers that Germany could no longer match. They were being defeated by an industrial system that could design adequate equipment and then produce it in quantities that rendered German qualitative advantages increasingly irrelevant as time passed and American production reached full capacity. The Americans designed to their industrial strengths, leveraging massive manufacturing capacity, abundant raw materials, and efficient logistics systems that functioned despite global scope. Germany, by 1943, was designing despite crippling industrial limitations, attempting to achieve through engineering cleverness what they could no longer accomplish through industrial might. The strategic implications were thoroughly documented throughout the Luftwaffe's technical services by the end of 1943, when the trends became undeniable to professional observers. Germany had entered the war with arguably the world's most advanced air force equipped with aircraft that were generally superior to their opponents on a one-to-one basis in direct comparison. German pilots initially were better trained than most opponents they encountered. German tactics were more refined based on Spanish Civil War experience and careful study of air power theory. But German industry fundamentally lacked the capacity to sustain these early advantages when facing opponents with vastly greater industrial resources and geographic advantages. American aircraft production doubled repeatedly. The numbers increased in 1940, again in 1941, again in 1942, and continued expanding until by 1944, American factories were producing over 96,000 aircraft annually. Germany never exceeded 40,000 aircraft in any single year despite desperate efforts to increase production through longer working hours, forced labor, and dispersal of manufacturing to underground facilities. The quality gap between American and German aircraft widened steadily rather than narrowing, as some German planners had hoped. In 1942, German aircraft were often superior to their American opponents in direct technical comparison. By 1944, American aircraft equaled or exceeded German designs in virtually every important category that mattered in combat. By 1945, the gap had become a chasm that no amount of tactical skill could bridge effectively. American fighters like the P-51H and P-47N represented evolutionary refinement of already excellent basic designs that had proven themselves in combat. German fighters like the Ta-152 represented desperate attempts to extract more performance from industrial systems collapsing under the combined weight of strategic bombing, raw material shortages, and the replacement of skilled workers with poorly trained forced labor from occupied territories. The psychological impact on Luftwaffe morale of facing endless streams of capable enemy aircraft proved as destructive as the material losses that mounted each month. German pilots reported feeling less like warriors in honorable combat and more like targets in a systematic destruction campaign designed to eliminate German air power through attrition. No matter how many Allied aircraft they managed to shoot down, more appeared the next day in equal or greater numbers. No matter how skillfully individual German pilots fought, American numerical superiority eventually prevailed through sheer attrition that no tactical brilliance could overcome indefinitely. The knowledge that their opponent's equipment was often superior to their own, delivered in far greater quantities, supported by better logistics, and flown by adequately trained pilots who were quickly replaced when lost, created a pervasive sense of inevitable defeat that spread throughout the fighter forces during 1944. The captured P-47s served as tangible physical evidence of this harsh reality that no amount of propaganda could disguise. These were not exaggerated claims in intelligence reports or propaganda photographs designed to boost morale. They were actual aircraft that German pilots could examine directly with their own hands and eyes. They could sit in the cockpit. They could study the instruments. They could examine the construction techniques and material quality. The Thunderbolt was not some miracle weapon or revolutionary technological breakthrough that represented unachievable advances. It was simply a very good fighter aircraft, properly designed for its intended mission, adequately powered by a reliable engine, well armed with proven weapons, appropriately protected by armor in vital areas, and manufactured in quantities sufficient to overwhelm opposition through systematic application of material superiority rather than technological wizardry. The final historical irony was that the Germans learned these lessons thoroughly, documented them professionally with typical German attention to detail, and grasped the strategic implications completely. Yet they could never apply the knowledge they had gained through careful study. Understanding American industrial superiority did not magically grant Germany access to the aluminum, steel, fuel, skilled labor, undamaged factories, and functioning transportation networks needed to produce equivalent aircraft in equivalent quantities. Knowing the P-47's exact performance capabilities did not provide Germany with the high-temperature alloys, precision manufacturing equipment, quality control systems, and trained workforce needed to build comparable turbo-supercharger systems. Intelligence gathered from captured aircraft documented the dimensions of German defeat with professional thoroughness and scientific objectivity, but it offered no realistic path to avoid that defeat given Germany's deteriorating strategic position. When Allied forces captured Rechlin and its associated testing facilities in May 1945, they discovered extensive documentation of the captured aircraft evaluation program that had operated throughout the war. German technical reports filled dozens of filing cabinets, detailing every measurable characteristic of every American and British aircraft that had been systematically examined during the conflict. The reports were models of technical thoroughness and scientific objectivity that impressed Allied investigators. They also represented thousands of man-hours spent meticulously documenting capabilities that Germany could observe and measure with precision, but never replicate given their deteriorating industrial situation and resource constraints. American technical intelligence teams who reviewed the German reports after the war noted with professional interest that German engineers had understood American aircraft capabilities more clearly and in greater detail than American commanders sometimes did in operational planning. The Germans had identified specific weaknesses in American aircraft designs that American pilots learned to work around through combat experience and tactical adaptation. The technical analysis was frequently more detailed and rigorous than equivalent American evaluations of their own equipment conducted for internal use. German engineering competence had never been in question throughout the conflict. The quality of their technical analysis remained high, even as their strategic position deteriorated. But the American reviewers also noted what the German reports implicitly revealed about Germany's increasingly desperate strategic situation. Germany had attempted to fight a modern industrial war with an industrial base that was fundamentally insufficient for the task they had undertaken. They had compensated initially through excellent engineering, superior pilot training in the early war years, and tactical innovation born of necessity and careful study of combat experience. These advantages had sustained them through early victories against opponents with similar resource constraints and industrial limitations. But against an opponent like the United States, possessing industrial capacity that exceeded all other major powers combined, excellent engineering and tactical skill could only delay the inevitable outcome rather than fundamentally change it. The mathematics of industrial warfare were unforgiving and absolute. The story of German engineers examining captured P-47 Thunderbolts provides a clear case study in the harsh realities of industrial warfare as it had evolved by the Second World War period. The Thunderbolt succeeded not because it represented the absolute best possible fighter aircraft by every conceivable technical measure, but because it was a very effective fighter aircraft produced in quantities that made isolated examples of technical superiority strategically irrelevant in the broader context. American industry built 15,683 Thunderbolts, while simultaneously building 15,486 P-51 Mustangs, 10,037 P-38 Lightnings, 13,738 F-6F Hellcats, and 12,571 F-4U Corsairs. Total American fighter production exceeded 70,000 aircraft during the war years. Each aircraft represented thousands of hours of skilled labor, tons of aluminum and steel, hundreds of precision components, and manufacturing capacity that Germany could not approach even under optimal circumstances. The P-47 Thunderbolt became a symbol of American industrial dominance to German pilots who fought against it in increasingly desperate circumstances. Luftwaffe pilots adopted the same nickname American pilots had coined, calling it the Jug in acknowledgement of its somewhat ungainly appearance that belied its combat effectiveness. They also called it Indianer, after the Thunderbird emblem many American squadrons painted on engine cowlings for identification purposes. As losses mounted and the strategic situation deteriorated month by month, some German pilots referred to it simply as that 8-gun fighter, and learned through bitter experience to avoid engaging Thunderbolts at altitudes where the American fighter held decisive tactical advantage. This increasingly meant avoiding combat above 20,000 feet, where the turbo supercharger gave the P-47 performance superiority that skilled German pilots could not overcome through tactical maneuvering alone. By the war's end, P-47 Thunderbolts had destroyed approximately 3,520 enemy aircraft in aerial combat, while approximately 3,499 P-47s were lost to all causes, including operational accidents, mechanical failures, and dangerous ground attack missions. This roughly 1-to-1 exchange rate in total losses appears unremarkable until one considers the context of how Thunderbolts were actually employed in combat operations. Thunderbolts served primarily in the ground attack role from mid-1944 onward, facing intense anti-aircraft fire during low-level missions rather than engaging primarily in air-to-air combat, where their capabilities were optimized. In the pure fighter escort role during 1943 and early 1944, P-47s achieved significantly better exchange rates, particularly at high altitudes where the turbo supercharger advantage was most pronounced, and German fighters struggled to maintain combat effectiveness. The ground attack role revealed yet another dimension of American design philosophy that emphasized versatility over specialization when possible. When P-51 Mustangs, with their superior range, began taking over bomber escort duties in 1944, the 9th Air Force reassigned many Thunderbolt groups to tactical air support missions supporting ground forces. The rugged P-47, with its reliable air-cooled radial engine and heavy armor protection, proved exceptionally well-suited for dangerous low-altitude attack missions that destroyed specialized aircraft. The same characteristics that made it seem ponderous in low-altitude dogfights, substantial size, heavy weight, comprehensive armor protection, powerful armament, made it nearly ideal for ground attack missions where survivability and firepower mattered more than maneuverability and climbing performance. Thunderbolt pilots flying ground attack missions destroyed staggering quantities of German military equipment throughout 1944 and 1945. Official claims documented through gun camera footage and after-action reports included over 86,000 railway cars, 9,000 locomotives, 6,000 armored fighting vehicles, and 68,000 trucks destroyed or damaged during ground attack missions. While such claims inevitably included some duplication and overestimation, the scale of destruction was undeniable and had measurable impact on German military operations and logistics capabilities. The P-47, armed with bombs and rockets in addition to its 8 machine guns, had evolved into a true multi-role combat aircraft capable of air-to-air combat and ground attack missions with equal effectiveness. German ground forces learned to recognize and fear the characteristic deep rumble of Pratt & Whitney R-2800 radial engines at low altitude. This sound provided warning of impending attacks that German troops were largely helpless to prevent given the lack of adequate anti-aircraft defenses. The psychological impact of constant air attack, combined with substantial material losses and the systematic disruption of logistics and communications networks, measurably degraded German ground forces' combat effectiveness throughout 1944 and 1945. The cumulative effect was a form of aerial siege that isolated German units and limited their tactical options regardless of individual unit quality or leadership competence. The question of what happened to the specific captured aircraft provides an epilogue to this story of industrial warfare and technological intelligence. William Roach's P-47D Beetle, serial number 4222490, designated T9+FK by the Germans, survived the war and was recovered by American forces at Göttingen in May 1945. After evaluation by American intelligence teams examining German testing procedures and results, the aircraft was eventually scrapped rather than preserved for historical purposes. Lloyd Hathcock's P-47D, serial number 4275971, designated T9+LK by German evaluation teams, met a similar fate, It was recovered by advancing Allied forces but not preserved for museums or historical study. The aircraft had served its intelligence purpose and was no longer needed for evaluation or display purposes. The pilot's fates after capture differed markedly in ways that reflected broader social issues within American society during the war period. William Roach spent the remainder of the war at Stalag Luftwaffe in Barth, Germany, a prisoner of war camp specifically for captured airmen. He was liberated by Soviet forces advancing westward in May 1945 and returned to the United States for medical evaluation and discharge processing. Lloyd Hathcock spent 11 months as a prisoner of war, primarily at Stalag Luft III, the site of the famous Great Escape that had occurred just 3 months before his arrival at the camp. He was the only African-American pilot among thousands of white prisoners at the facility, a situation that created unique challenges and social dynamics within the prison population. When Soviet forces advanced westward in January 1945, German guards evacuated the camp and forced prisoners on a brutal winter march to Stalag 7A and then Stalag 13D. Prisoners marched through snow and bitter cold with inadequate food and clothing. Many died during the forced march from exposure, exhaustion, and disease. Hathcock survived these ordeals and was liberated by Allied forces in April 1945. After returning to the United States, Hathcock played a significant role in the post-war desegregation of the U.S. Air Force and continued his military career. He later pioneered important innovations in aerial reconnaissance photography techniques at Wright-Patterson Air Force Base, contributing to intelligence-gathering capabilities during the early Cold War period. Hans Werner Lerche survived the entire war despite flying 125 different aircraft types, including numerous captured Allied aircraft throughout the conflict period. His remarkable safety record stands as unique in aviation history. He never crashed or seriously damaged a single aircraft throughout his test pilot career, despite flying experimental and unfamiliar aircraft under often dangerous conditions. After the war ended, Lerche provided extensive debriefings to Allied intelligence services about German aircraft development programs and testing procedures. His memoirs, published in German in 1977 and translated into English in 1980, provide one of the most detailed first-hand accounts of the German captured aircraft evaluation program. They offer valuable insights into how the Luftwaffe systematically assessed Allied aviation technology throughout the war. The broader lesson that emerges from the story of captured P-47 Thunderbolts in German hands transcends the specific technical details of one aircraft type or even one military service. The Thunderbolt evaluation at Rechlin demonstrated that by 1943, the outcome of the air war over Europe was being determined not by pilot skill, tactical innovation, or even aircraft performance in narrow technical comparisons, but by industrial capacity applied at national scale with systematic thoroughness. The nation that could design adequate equipment and produce it in overwhelming quantities, while simultaneously producing everything else a modern military requires for sustained operations, would inevitably defeat opponents who produce technically superior equipment in insufficient quantities to affect strategic outcomes. The mathematics of industrial warfare had become more important than individual technical excellence or tactical brilliance. Germany's position by late 1943 was that of a nation attempting to compete industrially against opponents whose combined industrial capacity exceeded German capacity by factors of 5 or more in critical categories. When Britain refused to capitulate after France fell, when the Soviet Union survived the initial German onslaught and successfully relocated its industry beyond German reach, and when the United States entered the war with its vast, untouched industrial base, Germany's path to military victory had effectively closed. The only remaining question was how long Germany could continue fighting and how much destruction would occur before reaching the inevitable conclusion that industrial mathematics had already determined. The story of Beetle and the other captured Thunderbolts at Rechlin thus becomes a microcosm of Germany's broader strategic dilemma during the final years of the war. German engineers could examine American equipment with professional competence, understand American capabilities through systematic testing, and accurately assess American industrial strength through careful analysis. This knowledge was professionally gathered, carefully analyzed, and thoroughly documented in reports that impressed Allied investigators after the war. But knowledge alone could not produce the aluminum, steel, rubber, fuel, machine tools, skilled workers, undamaged factories, and functioning railroads required to compete with American industrial output. The Republic P-47 Thunderbolt, examined in meticulous detail by German engineers at Rechlin, proved a final truth about industrialized warfare in the 20th century that transcended specific technical or tactical considerations. Material abundance, systematically applied through competent engineering and adequate tactical execution, would defeat technical excellence constrained by resource scarcity, regardless of individual brilliance or dedication. The most powerful element in America's arsenal was not any individual technology, however impressive its specifications, but rather the complete industrial system that could conceive, design, develop, test, produce, and logistically support thousands of complex weapon systems simultaneously. This system maintained quality control while continuously improving designs based on combat experience and changing operational requirements. The captured Thunderbolts taught this lesson with undeniable clarity to German observers who measured performance with scientific precision. German engineers documented American capabilities professionally and reported findings accurately through their chain of command to decision-makers who understood the implications completely. Unfortunately for Germany, this vital lesson arrived too late to matter strategically. By the time William Roach's Beetle was being meticulously examined at Rechlin in late 1943, the outcome of the war had already been determined by industrial mathematics that no amount of German engineering skill or individual pilot courage could overcome. The Thunderbolts, sitting on German airfields wearing hastily applied Balkenkreuz markings over American stars and bars, represented a future that had already arrived. It was a future in which industrial capacity had become the decisive factor in modern warfare, overwhelming traditional military virtues through systematic application of material superiority.